So what I said is, so let me start then. So
Yes.
I said that I would speak about, so I think first Carol said I would speak about integration with respect to the unitary group. And sometimes this is a particular case of something which is called a Weingarten calculus. So maybe I'm just going to, so as per the instructions of Carol again, I should be very, very elementary and maybe give some motivation and all that. So I will try to be, you know, as elementary as possible. And so the general context in which we are working is as follows. The general context is as follows. So what we do is we take a compact group G, a compact group. And what we do is we assume that this compact group is actually a matrix group. This is it's contained in the matrices. So here, you know, I'm going to put C, but you know, it doesn't matter. You could put R if you prefer. I mean, this is, you know, you can put, maybe you can put 2n of R or whatever, you know. So this is actually the assumption here doesn't really matter. And what I mean here is that the multiplication of the group is the multiplication of the matrices. So namely, what we have is that the group is actually a subgroup of GLN of C, which is itself here. And so this is, you know, it is a vector space. There is some topology, and compact is with respect to this topology. So some very simple observation first, but which will be really important for us, is that actually, so a fact is that without loss of generality, we can assume actually that G is contained in the unitary group. So which is, of course, the collection of matrices in GLN of C, whose inverse is the adjoint, so the transpose of the complex conjugate. And the reason is because every compact subgroup is contained in a maximal compact subgroup, which itself is conjugate to the unitary group. Well, you can, there are other ways to show it, but this is one way to show it. So what is always true is that, so what is always true? What is always true? True is that there exists some matrix W in GLN of C, such that WGW inverse is actually contained in UN. So you see, whatever I'm saying, oh, and by the way, WW inverse is invertible. So, you know, this is just like an invertible map from Mn to Mn. So the topology remains the same, everything remains the same. So what I'm just saying is that if I can solve a problem for a subgroup of UN, then I can solve for any compact group. But as we will see, it will be really useful to solve for UN. So I know that Carol asked me about UN, but actually I will treat slightly more general for many reasons. For one reason is that, you know, there are some applications which are interesting for more general groups. And another one is that actually the proof works exactly the same way. So I think it's a kind of makes sense. And the last thing is that actually this is the assumptions which we really need to have the theory work. So one thing which I perhaps should have said in the very beginning is that since G is a compact group, there exists, or maybe I should be checking the chat in the meantime. No? Oh yeah. Okay.
No, don't worry. Don't worry.
No, that's right. So please, anyway, yeah. Since I'm typing with my since I'm writing with my stylus, please maybe interrupt me in real time. Maybe it's the best thing to do. So the basic fact, the basic fact is that G, the compact group which I took above, admits a unique left and right invariance measure, left and right invariant probability measure, which I will call mu of G. So just to remember G. So it's a okay. Maybe I should say okay. So G is a compact group. So it has it has a topological structure. So it has a Borel algebra, and then so it's a measurable space, and there is a measure on it. So I can turn it into a probability space, and the property is that mu G of the group is 1. That's my normalizing assumption. And the second thing is that for every measurable subset of G, so this is a measurable, and for any G in G, then I have that the measure of G of GA is the measure of G of AG is the measure of A. So given that, maybe I should have explained this, that this is all the left translate. So this is the collection GX for X in A, right? And likewise, this is the collection XG for X in A. So this is the collection of all, well, I don't know, left translate and the right translate, I suppose. So if I rotate around, then this is what we have. So maybe some classical examples first. Some classical examples are some classical examples which are actually simple to compute. Of course, I could take S1. Okay, so S1, and then I would have I would have the Lebesgue measure here. Okay, so which is of course a unitary group. Okay, if I want, but anyway. Then I have also, well, classical is not maybe a good word. Maybe I should say some element, well, simple example, okay? Simple examples. So another example would be, it would be what? It would be a finite group. A finite group. And then I would have that, that the probability of an element. So the probability here is mu. So if mu G of an element G is just 1 over the cardinal of G, right? By the way, every finite group is, of course, can be embedded so in the unitary matrices, because every finite group can be embedded in the permutations by the left action, and the permutations I can look at the permutation matrices with 0 ones. They are unitary, so everything is all right. So the finite groups are also a particular case of what I'm going to say. And maybe one more example, which is non-trivial and and probably quite interesting for you and for me too as well, is SU2. SU2, which has the structure of the sphere. Okay, and here what we can check with not too much effort is that the uniform measure, the uniform measure is going to be the Haar measure. Well, the uniform measure satisfies the property of the Haar measure because if I make a left multiplication of SU2 by itself, it's actually an orthogonal transformation. So the uniform measure satisfies it. Therefore, it has to be the right one. So only the uniqueness is not completely clear here, but we just have to believe it from the axioms. And this one is slightly less trivial already, and somehow what we want to do is generate this kind of thing. And okay, so one observation is that the existence of the left but yeah, maybe I should have this. It's called the Haar measure. So of course the Haar measure exists in more cases. It exists for left and right, for locally compact groups. If you accept to give up either left invariance or right invariance, and then you have some conditions on whether it can be equal left or right, and then you have some files like it's finite if and only if the group is compact, and quite a few very interesting things. But the point is that what I would say is that the original proof of existence of the Haar measure are what I would call non-constructive, in the sense that it's a bit like the Lebesgue measure. Somehow, one way of doing it is maybe you can give some proofs with some outer measures, with some abstract measure theory, or another way, if you have which works for every locally compact groups, or maybe what you could do also is, you could for compact groups you could also even use some smart fixed point theory, but all this is not concrete somehow, and so all what I'm saying so far was done by mathematicians, I would say. So this goes from the beginning of the 19th century. Well, maybe 1900 is not good. Maybe like 1920 or so. Maybe something like this, and until the 1970 or so. And I would say maybe it's a slight overstatement, but I would say that this was mainly a mathematician's job somehow, a mathematician's job, and it was, the proofs of existence were non-constructive, mostly. The simple examples are constructive, but the other was not really constructive. Non-constructive. So what do I mean by non-constructive? I mean that if I give you a function on the group, so how am I going to compute the integral, right? So how to compute integral of f of g d mu g of g given f, which goes from g to r or to c, whatever, which is smooth, which is integrable, let's say. How to compute it? The proofs of existence of Haar measure don't tell you how to do this, and I think it's interesting to compare with Lebesgue measure. If you know how to compute the Lebesgue measure, maybe you don't know how to compute if you know that the Lebesgue measure exists, maybe you don't know how to integrate exponential minus x squared with respect to the Lebesgue measure, for example. You have, to develop some tricks which are independent from measure theory. So somehow this kind of things which are not answered. So again, a little bit of history. I think history matters here. So the first attempt which has been done here is some exponential functions. Some exponential functions. I will not spend too much time on it because this is not what Weingarten calculus does. Functions. So maybe I could say, I would be slightly more precise, but without developing the vocabulary, the Fourier transform, or the Laplace transform actually, of orbits. For the coadjoint action. For the coadjoint action, and this was done by Harishchandra. Am I spelling it right or not?
Almost.
Not sure. Almost, yeah. Okay, yeah. So then maybe.
And historical question: it was done more or less before the Second World War, or?
I think it was in the 50s.
50s. Okay.
I think it was in the 50s. I'm not 100%. I think it was in the late 50s. I think.
Yeah.
But I don't remember by heart.
Yeah. So I only know there is a very nice and famous Harishchandra Institute in India operating now.
Sure. Yeah. And so Harishchandra was one person actually, and his theory was actually rediscovered. So you see, Harishchandra, I think, he had exactly the problem which I'm mentioning somehow. Like he said, okay, well, how to compute some functions about it. And I suppose, I mean, maybe it's not exactly how he thought, but he said maybe we could just try to look at the Fourier transform first. Like if I can get the Fourier transform, I can get everything, which is true in principle somehow. But what is beautiful is that there was a very beautiful algebraic formula. So very beautiful algebraic formula, which I'm not going to give, but interestingly, again, assuming that there are many physicists in the audience, Itzigson and Zuber, they just looked again at the same problem in the case of the unitary group, and they got the same formula basically. So they had a completely different motivation. They were trying to see what happens when n goes to infinity. I think initially, they were interested not about the Fourier transform, but its logarithm, somehow see it as some partition function, which you can use when you try to get some toy model for quantum gravity. So the toy model is related to 2 dimensions. So it was. I think they were following up on some ideas of 't Hooft. So they got a similar formula. So quite often nowadays it's called the HCIZ integral, Harishchandra Zuber. So 't Hooft, he started to look at this in the early 70s, and actually, so 't Hooft himself, what he started to look at more precisely, he said, well, let's look at classical series of groups. So maybe I'm going to copy what he was trying to do again. So what he was trying to do is to try to integrate polynomial functions on classical groups, So what I would say is that he was interested in G is the unitary group, the orthogonal group, or the asymptotic group, something like that. He was interested in this series A, B, D of D groups, and try to see what we can say about such functions. So he was looking at this integral of ui1 j1 and so on and so forth with respect to the Haar measure on G. So maybe I should be a little bit more precise, because that's actually what I'm going to describe later on. So what I mean is that the way we're going to do from now on is G, quite often I will call it U because I'm going to assume it's unitary. And so it's a matrix which has some entries Uij. So what I do is I'm really thinking of Uij. I'm making some kind of abuse of notation, and Uij is a function from the group to C, which just to G, associates the ij entry. What I'm just doing is I'm looking at the ij component function, and then actually this is what I should call the polynomial functions on G. And then he said, okay, let's try to look at the integral of every polynomial. So which is of course not what Itzik and Zuber, Aristotle were doing, because they were looking at exponential functions. So here is polynomial functions. It's a very, so what he's been trying to do is very natural in my opinion, because this is a compact group, and if you're able to compute all these integrals, then by Stone-Weierstrass theorem, then you can approximate in norm every continuous function. And if I know how to approximate every continuous function, I know how to integrate every continuous function. And then by a Ries-Brettingen theorem, it means that I know how to, I understand completely the measure, because understanding a measure is like understanding its integral against every continuous function. So there is just one thing where I lied here. These are, of course, in continuous polynomial function, but I should also allow some other kinds of functions, which are the conjugate functions, ui prime 1, j prime 1, something like this, because sometimes I will need them. And actually, here is a very simple example where I would need them. It's in the case of S1. You see, what is U11 is just the function z. And then if I want to calculate what is the integral of z, then this is 0, right? Because integral of z is like integral of some rotation of z, or minus z, whatever, and then it's always going to be 0. And same for z square, same for z cube, and all this. So if I don't take some bars, then I will always, in some cases at least, in the cases where I have some S1, some rotation invariance of the group, I will always get 0. So not for the orthogonal group, but for the unitary group, I would have such a property. So it is important to allow some bars as well, some conjugates. Maybe I make this. The conjugates are allowed. Conjugates are polynomials, which is and by the way, also it's also completely compatible with the general statement of Stone-Weierstrass theorem. Stone-Weierstrass theorem, it really speaks about some real algebra. So we really need to introduce the conjugates as well for the statement about separation to make sense. So actually, this was initiated by 't Hooft, but very soon, Weingarten, who was perhaps one of his own, but I'm not sure actually. So Donald Weingarten. he wrote 2 or 3 short papers. You know, for a mathematician, it's very mysterious because it's like a four pages paper with lots of beautiful ideas in it, but the proofs are not completely complete, and you know, you have to understand what's going on basically. But what Weingarten did, so actually he also dealt with all these things. What he did is he just looked, you know, he just computed and something like this. He computed maybe what I will just do is I will just write his theorem. Let me just do this. Let me just write his theorem in the case of UN. So he did a bit more, but G equals UN. So what Weingarten did is he said, okay, let's compute UI1 J1, UIK JK, U bar I prime 1 J prime 1, U bar I prime K J prime K with respect to the Haar measure on the unitary group with respect to, let's say to U or to G here. And what he said is the following. He said that what you have to do is try, okay, sorry. So one more thing before I start writing the answer, the theorem actually. Here you see, I did one thing special is I took the same number of U's and the same number of U bars. And the reason is because if I had not done so, then the value would have been 0 by the S1 invariance. If I replace U by EI theta U, then it's the same distribution, right? It's the same distribution by rotation invariance. So let's say I take theta irrational, anything like this, then immediately you see like maybe I rotate K times in one direction, and then K, if it's not the same amount here as if it's K prime, then I go back K prime times, and then it has to be 0. So we need the same amount here to obtain something non-trivial. So this is here the same number of U and U bar. Doesn't mean again, just to repeat, doesn't mean that it's not possible to do it in other cases. It just means that in other cases it's trivial. We already know the answer. And so what he observes that in the only non-trivial case which is left, which is this one, he observed that you should actually check the row pairings between U's and U bars and the column pairings between U and U bars. So the row indices, this is I for U and I prime for U bar. And so I should check if I can make one pairing between some I and some I prime, which means I can say like, you know, number first guy is equal to last guy, second guy is equal to penultimate guy, whatever. I should try to see if I can find some arrangements which make some matching, which means that I should have some permutation of SK of some Kronecker function like this: I1, I prime, sigma 1, IK, I prime, sigma k, and the same for tau. So for the same for the row indices. So again, SK, and I'm just going to write below, why not? Delta J1, J prime, tau 1, JK, J prime, tau k. And so what I do is I check all the pairings, you know, all the pairs of pairings. And if I get a match, so let's first start with something simple. If I don't get a match, then I forget it. You know, like one of these numbers is 0, and then I don't count it. But if I have a match, then I have a function which will obviously depend on n, and it will actually also depend on sigma, on the pairings. And that's my integral. So what actually Weingarten did basically is he proved that there exists such a function. So what he proved that there is such a function for n large enough. That's his result basically.
By the way,
he said,
Benoit, do you recall more or less when this original paper by Don Weingarten was published? Like 60s,
yes.
70s, 80s?
78.
78?
Yeah.
I see.
78. I remember it because this is the, it's the paper who gave me a job basically. I was trying to understand this paper, and then, I tried to write down some details and get some formulas and whatever. And so, yeah, I mean, I lost lots of hair on this. It's not obvious, but I lost lots of hair on this.
Yes,
on this.
But strangely enough, it is not quoted in your recent pedagogical paper on Weingarten calculus, I presume.
I think it is.
It is? Okay, I will check it. I will check it. Okay.
Yeah, I think it is. Yeah, no, I would. I wouldn't dare not quoting it. Yeah, this is actually.
Can I?
Yes, please.
Oh, sorry. Continue. I just wanted to ask a short question, like on the. So in this product with this UIJ, if I understand correctly, so this is like every UIJ is essentially an entry of unitary matrix, and you just take the product over different entries. So I don't know, U11 times U22, and then you need the bars. So it would be, I don't know, U21 of bar times some other bar, and then you need the same amount.
Yeah.
So it's really not a matrix product here, but just a product of the numbers that are
entries
in these matrices.
Exactly. Yeah. It's really of entries. Yeah. So you see, the thing is that later on, but probably I will not discuss it today. Later on, what you do is you are indeed interested, depending on which kind of applications you have in mind. You are maybe interested in taking the product of matrices, and in this case, the only thing that we are able to do with Weingarten calculus, what we know called Weingarten calculus, is expand, apply this formula, group the terms, and hope for from some nice pattern, from some nice asymptotics, and so on and so forth. So
just to continue, so to make it simpler, if those yellow products will continue of one element only, you could have like Uij and now Uij bar, which is like modulus of Uij squared, which we know that it should be equal like 1 over n.
Yeah.
Yeah. So is it easy to show that with this Weingarten calculus you get such a nice result?
Yeah.
Okay.
So you see, if you let's so if you want, maybe I can just even give 2 or 3 examples. You see, like if I want to calculate
I think for this is very good to see an example.
Sure. Okay. So let's do some. So if I look at this, if I want to compute this U11 bar.
Yes.
Then I just have one pairing. You see, yes. I just have. So let me try to put some colors. So I have the pairing. Just this pairing for the sigma, and just this pairing for the tau. So I just have one pairing, and in this case, what I get is that this is the Weingarten of E, so N E E. That's it, which turns out, as you guess, to be equal to 1 over n. Right? Because, so why is it 1 over n, by the way? Because U11 bar is the same as U12 bar, right?
Yes.
And they are all the same, but then we have orthogonal. So like n times it is equal to 1. So it has to be 1 over n. And so another example would be this integral U11 U bar 12. This would be 0. Because you see here, I could get one pairing, but here I could never get one pairing, whatever I do.
Mhm.
And right, so maybe let me give one more. I think it was the one which was mentioned by Felix. It was U11, U22, U bar 1, 2, U bar 2, 1. So here, this one, I have only one pairing. So, which is like, you see, this is going to be sigma, which is the identity. And the tau is going to be the swap between 1 and 2. If I want to, you see, if I want to match the row index, the row indices, then I have to match the first one with the second one, and the second one with the first one. And then, so I have only one thing, and this is, so here this is in my notation, but it's a cloud notation which I will improve very soon. WGN of E and 1, 2. And here, this is known to be what? I have to remember. This is -1 over n -1, n plus 1. Okay, this is this quantity. By the way, let's make some comments. Here. First of all, you could say, but we have a pole here. That's not very good. You know, like a mathematical pole, of course. You want me to make some funny jokes. So -1, n equals 1 is a pole. But of course, because this makes no sense for n equals 1, right? This equation makes sense as soon as n is bigger than 2, right? So there is no inconsistency here. Something else also which
bigger or equal or 2 or bigger.
Yeah, equal or so for this makes sense for n bigger or equal to 2 here.
Sure.
So what Weingarten actually, so let me get back to this. What another thing which Weingarten showed is actually this depends only on the conjugacy class of sigma tau inverse. So it does not depend on sigma and tau. It depends on the conjugacy class. And then a little bit more of history. Maybe, yeah. So maybe I will spend lots of time on history, but that's all right anyway. We know we do whatever we. So actually, well, together with well, okay. I got a formula that okay. So then Collins 2003, followed by Collins and Schneidi in 2006. We got some formulas. So maybe I would say, I mean, it's kind of difficult to, but I would say that I got a formula for n bigger or equal than k. So not n large enough, and I got some actual formula. Some formula, I should say, for the Weingarten function, and together with and in the unitary case, maybe probably it's fair to say that, and together with Piotr, we got a formula for actually any n and k, and in un, on, spn. That's basically how I would, and I think so. I was doing my PhD during that time, and I think that historically, Weingarten, he called this function phi. I think he just gave a name to this function. Maybe it was phi, and my supervisor Philippe Bien told me, yeah, you should name it after Weingarten. So maybe you should put something like WG or something like this, and we should call it Weingarten calculus. So this is how it was born, how it was named, at least. Right. By the way, so I got this formula for Weingarten, for the Weingarten function. It turns out that actually Zuber and Brezin, they also obtained almost the same formula, but maybe not with this constraint, in the 80s. But it was at the time, so my formula, I obtained it around 2000, and it was still a time where, it was still difficult for mathematicians to see what physicists had written and so on and so forth. Actually, Zuber was my PhD examiner. So he taught me lots of references about physics which I didn't know, and he really enriched my knowledge quite a lot. So anyway, so this is the history, and so yeah, something which is important as well. Probably not have too much time to speak about it today, but something which is really important is, and yeah, I would say that this was really also the important idea of 't Hooft and Weingarten is, you see, in principle, when we see this, we are trying to solve it for a fixed n, right? Like I have n, I have a group, and then I try to solve this. And here the approach is different. Is I have this thing, and it makes sense for any n which is large enough. So of course, like the functions, they change because the group, they change as well. But I have a consistent way of defining it as soon as n is large enough. And it is very interesting to understand how this behaves. So behavior.
Sorry, yes. But this result 1 over n is exact for any n, not only for large n.
It's exact, yes.
Okay.
This one is exact as well.
Yeah, sure. So you have like 15 more minutes, okay?
Yeah, I will do whatever I can, and then I will stop. So behavior of the behavior in the large n limit. In the large n limit. So maybe what I could do is try. I think I promise I will do it. So I will try to do it. I would like to try to explain how to compute, how to get such a result. So how to get such a result. And well, maybe I will be a little bit sketchy, but hopefully you get the idea. So what we would like, basically, what we do is we introduce, so we introduce U, a matrix which is in Mn of C, and I'm going to take a point of view of probability. So this is a random matrix. This is a random matrix, and its law, its distribution, is the Haar measure with respect to G. Okay. So now I say, okay, let me just try to study a random vector, because of course this is a vector space. So I study a random vector whose distribution is mu of G. Okay. So I'm actually not going to study one random vector, but two random vectors. I'm also going to study U bar, which is the entry-wise conjugate. And I take all. So it's not the inverse. This is the entry-wise conjugate. What you need to remember here, that the map that from U associates U bar is a group morphism. This is actually the link to the adjoint action, basically. So and this plays a big role. So I'm looking at this random matrix and that random matrix. And now what I want to do is actually, our problem boils down. So our problem of integrating, of computing such functions boils down to computing the expectation of u tens k tens u bar tens k prime. So which is a matrix in Mn of C tens k plus k prime. Let me explain. U is a random matrix, so it's a random vector. So U tens K is also a random vector in a tensor, in like a tensor product. I still have a vector in a tensor product. Likewise for this. So this is a random matrix. It's a random vector in a big space, right? And it's bounded, of course, because this is a unitary matrix. It's a unitary matrix, so the whole thing is unitary. It's bounded. So I can take the expectation of this. The expectation is a matrix. And what I'm just saying is just reformulation of what I have above is this matrix actually, this expectation, if I look at its matrix coefficient in the canonical basis, they are exactly these functions which we want to compute. So I'm just doing some kind of quantum trick. I'm saying, okay, let's compute them all at once, okay? And this turns out that it will be simpler, It's really like, it's really like quantum computing. We just compute everything at once, and then we get the result. So, so I will just give a name to this. This is going to be the matrix Z, K, K prime. If I give you a formula to compute Z, K, K prime, and if this formula is not too ugly, then you have solved the problem. By the way, so at this point, I should say that I am actually back. I'm actually back to a general G. All right. And well, so the first observation is that actually Z K K prime is self-adjoint. So again, since I have only 7 minutes left, I will probably be a little bit skippy. But why is it true?
Could I very quickly ask? So this expectation, is it like the trace of this integral over U tensor K tensor U bar, or what?
Not even. It's just, you see, it's a vector. It's a random vector.
Oh,
I just take the expectation of the vector. So this is the matrix, right?
So it's sort of the integral over this expression over the unitary group or the group that.
Yeah. Okay. Exactly. Yeah. So see, this is a random matrix. So if I take its expectation, this becomes a matrix. It's I know it's a bit counterintuitive from a point of view of random matrix theory, but this is that's what, like, if you take just to clarify, if I have a GUE, if I take its expectation, I get 0, which is not interesting. But here it's interesting. And actually, the very reason why it's interesting is because we get tensors. So first observation is that this is a self-adjoint. It's a self-adjoint operator. And here, so very briefly, it's because the change of variable G to G inverse preserves the Haar measure. So if I make a change of variable G to G inverse, then I get Z replaced by G star. And then this is, and then that's good, okay? So like G inverse. So this made a change of variable G to G inverse. Observation 2 is actually Z K prime is a projection. And here, to prove this, I just make a change of variable like this. G replaced by U times G. And what I get is Z K prime equals U times K times U bar times K prime times Z. And then I reintegrate once more. So this is a projection. So now you see the situation is kind of good, because if I know that it's a projection, then if we know the image, we are done. Okay. If I want to write a projection, it's enough to know its image. And an orthogonal projection is enough to know its image. So a simple observation, which is the observation 3, is that actually the fixed points. So I will say that fixed k prime, which are the collection, the vector x in C n tens k plus k prime, such that u tens k tens u bar tens k prime of x equals x. The points which are left invariant by this is contained in the image of z k prime. This is very clear, right? Because of course, if it's invariant under u, then for all u, then if I average, this is again invariant. Then z of x equals x, so it's in the image. And the last observation, which is it's one which I really like, and I've never seen it really written anywhere, is that actually fix. It's written somehow, but maybe with not such a simple argument. Fix k prime is actually to the image of z k prime. And here, let me just draw a quick picture. Let's assume, you see, this is my tensor space. Okay, this is my big tensor space. I have 0, and let's assume that I have a guy which is not invariant. So like I can find, I can find a vector u such that it gets moved a little bit like this, right? If it gets, now what we use, what we have is if it can get moved by at least one u, then maybe it can be moved in a neighborhood. And then if I take the expectation by strict convexity, the expectation, so if y does not belong to fix k prime, then what we will have is that the norm of z k prime y must be strictly less than y. This is the strict convexity of the Euclidean norm. You see, if I move a little bit around, then if I take the expectation, it has to go down. So which means that actually this is exactly the fixed points. And then basically we are done. So then what we are left is to find generating family for fix k prime. And here, this of course depends. This is where the dependence on G occurs. And let me give some example. So we'll give the example for the example of u of un, and I think I will just stop here. So if I take Cn tens Cn, which is the case k equals k prime equals 1. And in this case, what do I have? Is that I have E, so let's say it's EI is the canonical basis of C. Then I have E1 tens E1 plus En tens En is going to be a fixed point. This is just the orthogonality relation. So this is the Bell state, multiple of the Bell state, which is a fixed point. If I take K equals K prime equals 2, then what will I have? I will have something like this. I will have what I could have is something like this. Sum for I and j between 1 and n of ei tens ej tens ei tens ej, or I could have some ij between 1 and n, ei tens ej tens ej tens ei. And this is again the orthogonality equation. You see, each time when I check what it means, when I sum over I get a row orthogonality for the, I'm just pairing the first u and the first u bar, and then I get an orthogonality. And same for the second one. And this, each time, what we see is that this corresponds actually to some permutation. This is the identity permutation. This is sigma. So this is 1 is sent to 1, 2 is sent to 2. I should keep in mind that, the first guys and the last guys, they play a different role. And here this is, because here I have some u's which play a role, and here I have some u bars which play a role. And here this is 1, 2. So this is here sigma is e, and here this is sigma is 1, 2. And the fact is that here I just gave you the example for k equals 1 or k equals 2, but this is always true. This is always true. And this is something which is called Schur-Weil duality. And then what you have to do. So you see, and I will just finish. I stop writing because I'm over time already. So the thing is, of course, in linear algebra, everybody learns how to compute orthogonal projection. But in general, the formula which we teach the most to our students is if we have an orthogonal basis, then it's very simple. Project the first vector, second vector, divide by norm, and this is it. Here we have a problem. The problem is that this spanning family is not orthogonal. So how do we solve it? We solve it by computing the Gram matrix and the inverse of the Gram matrix. But there is a formula. There is a very simple formula to compute the orthogonal projection onto a span of family which is not orthogonal. And if you write it down, you see that you exactly get this kind of things here. So what I should have said, maybe so Carol, can I have 2 or 3 more minutes, or is it not a good idea?
Okay, 2.5.
2.5. So let me just explain how you would make the calculation for again k equals 2. I will just give you the recipe, and then you just try to see how it works in general. So for k equals 2, I have 2 permutations. I have the identity permutation. Okay, so I have the identity permutation, and I have which I'm going to write like this. I'm sorry. The identity permutation is going to be like this. Okay, and I have the 2, 1, 1, 2 permutation. So what I do is I just create a 2 by 2 matrix, and what I do is I'm going to calculate the Gram matrix of these spanning elements. And here it turns out that how do I calculate it? So I put this guy above, this guy below, like this. So here I do the same, this guy above, this guy below. So here I do this guy above, this guy below. See, all these guys, I copy them below, like this, right? This guy above, this guy below, and I count the number of loops. So here I have n square loops, which is the scalar product of this and that. Here I have 1 loop, which is n power 1. Here I have 1 loop, which is n power 1. And here I have, oh, by the way, you should think that this is sigma and this is tau, okay? So this is sigma and tau, okay? And here I have n square. Then I have this matrix, n square, n square, which is my Gram matrix. I'm going to compute its inverse. And I can tell you by heart the inverse. The inverse is 1 over n square minus 1, 1 over n squared minus 1, minus 1 over n squared minus 1 times n, minus 1 over n squared minus 1 times n. You just ask Mathematica to check if you want, okay? And that's it. That's the end of the talk. This is the Weingarten coefficient, Weingarten n sigma tau. That's all. So now I told you how to do it for 2. If you want to do it for 3, 4, 5. So for 3, you will have to write a 6 by 6 matrix. For 4, you will have to write a 24 by 24 matrix. Of course, you don't do it. You just ask Mathematica to do it for you. And now you can calculate every integral of polynomial on the unitary group. Et voilà. Dziękuję bardzo.
Merci, monsieur. Arigato. Domo arigato. Thank you very much for a great talk and explaining us a lot of things. So I would love to ask many questions, but maybe let's first me ask, yes, Felix raised his hand, yellow hand. Please, Felix.
Well, it was a clap question, but I have a question as well. It was a clap sign. Thanks for the nice talk, Benoit. I was wondering, so actually I have 3 things, but like the first thing that you said with the that the local compact groups, is it admit a unitary representation? That's the one of the first facts you use, right? Is this Unitarian trick or unitary trick?
Yeah, so that's maybe it's maybe even a better approach, like you say. Yeah, you could say if you just use the existence of the Haar measure, then you take whatever scalar product, you average it, and then you see with this scalar product you're going to get something which is unitary. That's one way of doing it. Yeah.
And another short question, like this entries with these circles, that's the scalar product between permutation, right? Like the trace of sigma times.
Yeah.
Okay.
Exactly.
So,
yeah. So this is probably, you see, if you compute the scalar product of this and this, you just have n degrees of you just have 1 degree of liberty of freedom, which is the degree of freedom is the number of loops.
Yeah. Okay, cool.
Fine. Any further questions from the audience?
Yes, I have a question, if you don't mind.
Go ahead, Oliver.
So thanks for the talk. It seems like a really cool, tool to use, and it seems very powerful, what you presented. I wonder if you had any favorite examples of people using this stuff to solve cool problems, how does it get applied, or has it been applied in any interesting way yet?
Sorry, so to solve what? Sorry, I'm not sure I heard you. Applications, you mean, or?
Yeah. Do you have? Are there any nice applications that it's been used for? Do you have any applications in mind that this could be used for?
Yeah. So you see, I know maybe I was too slow at the end. I think it's the fault of you have to blame Carol. But actually, initially, the application which I had in mind personally was to prove something which is called asymptotic freeness of random matrices. So you see, if I have some matrices which are whose eigenvectors are randomly distributed with respect to each other, then if you take the product, they have some behavior which was predicted by Voiculescu's free priority theory, and you can prove it just with the help of this tool, basically. So this is the original proof by Voiculescu was actually quite involved. But there is a direct proof with moment computation, which was really my starting point. Then you have lots of applications in quantum information theory. You see, as soon as you have some random evolution, according to the Haar measure, if you want to see what's if you have a quantum channel which involves some Haar interest, and if you want to see some kind of behavior, you have access to the moments through this technique. So this is very useful. That's also how I got into there. Patrick Hayden at some point had some showed me an operator, and he told me it looks, mathematical simulation indicate that the spectrum should be like this, and I found it interesting. I just computed the moments, and that's the moments just give things. Then Karol Dziskowski told me, we could also apply it to these many interesting problems in quantum information theory, and then again you compute the moments and you get some answers. So you have lots of applications. There are also applications to quantum groups, for example, like all this theory which I said here. I just explained it for classical groups, but it works mutatis mutandis for quantum groups actually. And it's interesting because, for example, Voronovich, he had some formula for the trace, you see, for the threshold functions, but his formula can actually be extended to non-threshold functions thanks to this technology. So this is something which we did with Banica and others, for example. So Speicher has also been working a lot on it afterwards. So yeah,
Right, cool.
Thanks. Just some sample of applications.
Yes, thanks. Any further questions?
A very short one.
Yes.
I'm curious, whether the integration over the Clifford group has been done, but like a specific version, that one that Michael Walter and David Gross and so on use in their. They sort of do a sure-val duality for the Clifford group, but with a special diagonal action.
Maybe not actually. That's a very interesting question. I'm not sure it has been done actually. So maybe one way to reformulate your question, and actually some people are interested in this. Basically, what I said here is, from a point of view of British theory, what you could say is basically you just take the fundamental representation of the group and then you look at polynomial function on the fundamental representation. But of course, you could ask about functions on other representations. And you could argue, well, it's the same in principle. But of course, like you get maybe you have other paradigms, and then you have other formulas and other results. And that's a line of research as well. So I suspect that your question would fit in this framework, but I don't think it has been done.
Okay, cool.
Good. So Benoit, I wrote in chat a reference to some other papers by Pierre Mello, which is kind of known in our community. The origin was solid state physics and fluctuations of conductivity, but he also computed averages of a unitary group in the 80s. So I found the paper from 89, but he did it in early 80s, I presume. But now a simple question. We don't have much time to go into details, but what changes concerning the simplest results if we integrate over orthogonal group and not unitary? For instance, of course, O11 square is also average 1 over n, yes? But the other more complicated averages will differ, yes?
Yes. Okay, so if you want, I will do the orthogonal group for you. It's almost the same. It's almost the same, except that you don't need. You are not going to have two pairings here, so you are going to have the same pairing, but you have one more O. You have one more. You have one more, which is this one. You have this one because you see what you did here is you linked some U with some U and some U bar with some U bar, which is forbidden in the complex world.
Sure.
But in the real case, it's not forbidden because we don't make a difference between U and U bar. And then what you get is you get n square, n square, n square, n, 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 n. Yes. You compute the inverse. Okay. And then the inverse is, I don't remember this one. I think it's like 1. I think it's n minus 1, n plus 2, I think. And then so like this 3 times, and then I think it's going to be I'm
okay,
not sure. Maybe it's this
I see the main difference. So basically, strangely enough, this matrix becomes larger, even though the space is smaller, because you add some additional, you consider additional cases.
But you know, it's normal. It's normal. It's normal because if the group becomes smaller, you have more invariance. Okay. This is the basic of group theory. Yeah.
Mm-hmm. Very nice. Yeah, because this is also of some interest for us. We sometimes work with unitary groups. Sometimes we restrict our attention to orthogonal. So, Benoit, thank you very much for being with us so late during the day.